Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis, and we're in Chapter 7, part of this playlist called Classification Analysis, and we're actually in the penultimate video for Chapter 7, and penultimate is a math term which means second to last. Now let's jump to today's topic, which is classification trees. And the notation and terminology is going to be borrowed from a tutorial on RPart. RPart is a package in the R software, and it's called Introduction to Recursive Partitioning Using the RPart Routines. It's by Thurno and Atkinson, 2022. Now, originally, I had a list of things I wanted to talk about, but I didn't really like it. It seemed too boring. So I created a classification tree, and I'm going to talk about those bullet points, but point back to this tree. Now, when you look at it, there's like center points, and those are called nodes. So this is called the root node because it's the start of the tree, and then it branches off into two child nodes. So this is a leaf, it's at the end of the tree, and this child node becomes a parent and has two child nodes, and this one's a leaf, and this one has two child nodes. Now in reports or summaries, they number each of these nodes, and you have to know the numbering system. So the root is always node 1, and the rule is that the child nodes become 2x and 2x plus 1. So if this is 1, this is 2, 1 times 2, and this is plus 1, which is 3. So 1, 2, 3. Now the child nodes of root 3 become 6 and 7. The child nodes of 6 become 12 and 13. And so in the report, if it's talking about the properties of node 6, you noted that it's this one. Now, each node gets an impurity score. And what that means is how pure is that node? Okay, so for instance, this bottom right, there's 0 in group 1 and all 14 in group 2. So that's pretty pure. So the score of this would be 0, which is the absolute best you can do. Now the parent node here is there's 8 in group 1 and 31 in group 2. So that's a mixture. And in a classification tree, you want to come down to the end where all the observations are in one group, because then assign it to that group. Well, that's not usually the case. So for instance, on node 2, we have 24 in group 1 and 1 in group 2. And that's pretty good, actually. So the impurity score of this is going to be close to 0, not 0, but close. And the root of 32 and 32, I mean, that's as mixed as you can get it. That's the same observations in each group. So the impurity associated with this is going to be pretty high. So that actually leads to, how do you know to split a node into two child nodes? What we do is we look at the impurity score. So it goes through all possible combinations of splitting the data, and if the total impurity of the two child nodes is less, it will be less than the impurity of the parent node. And then we look at which one creates the best, or the best change in impurity scores. Each split actually will be a reduction in total impurity score, but there's some sort of best reduction, and that's the one we search for. So it's sort of an optimal criteria in this split. Now, the the tree grows until it meets some sort of stopping criteria, because we could grow this tree until there's only one observation in each leaf. But that's a silly classification tree, and the variance associated with classification is just too large. So you have to do what's called prune some of the branches back into something that's more reasonable. Two pieces of information on how to create child nodes which we're not going to consider because to keep the video at a good length, is what's called prior probabilities associated with each group and the misclassification of, or the cost of misclassification. And we're going to assume the cost is the same on, the misclassification cost same, and the prior probabilities are equal or proportional to the group sizes. Now, what we just covered were each of these. There's an impurity number associated with each node. 0 is the best. The higher positive numbers are worse. We look at all possible splits to create child nodes. If x is the node number, then 2x and 2x plus 1. The tree grows until it meets some sort of stopping criteria. Sometimes we have to prune the tree back to make it the variance associated with classification less. And prior probabilities and costs of misclassification will not be factored into this video. Now, how to calculate the impurity of a node using the Gini index. Now, there's other indexes, but Gini is the most common, most popular. And there's variants of this, but this is the most popular. So when we look at the impurity of a node, we have to call it something. So we call it node A. And the impurity looks at how many observations are in each group. Now the goal is to have all the observations of a node in one group. The impurity score would be 0. But if there's several groups with observations, then we look at the proportion of observations in group I, take it times 1 times that proportion, and then do that for each group and add them up. And that's the impurity score. That's it. It's kind of a simple index, but so powerful in what it can achieve. Now notice that if there's only one group with observations, all these PIs would be 0 except for the group that has observations. And it gets a score of 1. And so 1 minus 1 is 0. So the impurity is 0. That's the best you can do. Now, when the change in total impurity for a split of a parent node, that's the criteria that we use to split a parent into children. So we look at the impurity of the parent, and then it's the sum of the impurity scores for the child nodes. And we take that difference. And then we consider all possible splits until this change in impurity score is maximized. We want the split that creates the smallest impurity in the child nodes. Now let's look at an example. This example I've carried over through all the classification algorithms so we can compare them. And the data is from an FTP site given at this location. The data we use is T617 fish data. And Baden, Tack, and Bader look at compared judges' scores on fish prepared by 3 methods. 12 fish were cooked by each method, and several judges tasted fish samples and rated each on 4 variables. Each entry is the average score for the judges on that fish: aroma, flavor, texture, and moisture. So here is how we do it in R. Now, one thing that I always like to do, I like to recreate the function. So the built-in function is called rpart, and it's in package rpart, which is recursive partitioning. So what I want to try to do is reproduce at least some of the results to get an idea for myself on how it works. So we read in the data. There's no header, so we give the columns labels: method, aroma, flavor, texture, moisture. We print out the first 6 observations, and we look at this and we calculate the Gini index for a node. Okay, so we would send it the classes for that node. So CLS stands class, and it would table that, which calculates the number of observations in each class. and then divided by the total number. So we get a proportion of observations in each class. We multiply it, using the Hadamard product, add them up, and that's the impurity score. Now the total impurity of a split I call T impurity, and there's two pieces, right? So this piece, we calculate the impurity of a split. Now it goes through all possible. So for each possible split, we get an impurity score from one of the child nodes. And then this second piece, it adds it to, we look at the impurity of the opposite, right? This is less than or equal to that split, and this is the greater than that split. And so we get an impurity score. Now let's use these to calculate total impurities, So we feed it in the second variable, which is aroma. We have to send it the classes for each of those. And we get an impurity score for each split. Now somewhere in here, there's a minimum impurity score, and it looks like it's 27. So 29, 20, this one's 66.618. This split, we would split on aroma of less than or equal to 4.9, and the total impurity of that split would be 0.618. Remember, but we have to do this for all possible splits. So we do it for flavor, variable 3. I'm not going to reprint it, and it finds we would split on 5.5. The impurity, total impurity, would be 0.45. So actually, this so far is a better split to split on flavor at less than or equal to 5.5. We do it for texture. We get an impurity score of 0.6, which is still more than this one, so we still use that split. Then we do it for moisture. Well, it turns out that splitting on flavor is the way to go at 5.5 or below. Now, if we look at the unique numbers in flavor, these are it, and it says the split on 5.5. So 5.5 and below, and 5.7 and above. That's the split. Now let's see what our part does. We model method in terms of aroma, flavor, texture, moisture. We have to tell it class, method is class. There's 36 observations, and here's the information. So we have node 1, 2, 3, 6, and 7. And then this is information associated with each node, which we'll go, we'll just look at the plot and go over it. So we plot it, and we get this. A couple notes. The first split is at flavor greater than or equal to 5.6. So I want to go back and see how my algorithm looked. It said split at 5.5 and below. That algorithm said 5.6 and below. So that already tells me, me using an actual observation for the split is probably not best. It probably picks an average between those two splits, so that way you get a clean cut above and below. But the R part algorithm said 5.6 and below, and above 5.6. So it's actually the 100% the same classification. It probably just does it better and more efficiently. But anyway, to me, I get a good feel of how it works by programming it myself. Here there's 3 groups, and there's 12, 12, and 12 in each, so the impurity score associated with it is going to be large. The first split, it creates an 8 observations in class 1, 3 and 2, and 0 in class 3. So it assigns, if you end up here, it just gives you a class of 1. That's what it predicts. Over here, the next split's on texture. In node 3, there's 4, 9, and 12. It's actually, the impurity would be pretty high. The right node, it's 0, 2, and 10, and you classify it as class 3. And over here it's 4, 7, and 2, and you'd be classified as class 2. Now notice it stopped, so it met the stopping criteria. Let's look at how it does to predict. So we called resubstitute. So we use all the data to come up with this classification function, and then we resubmit each observation one at a time to see how it does on itself. And this is it. So the actual is on the left here, and the predicted by this classification tree is on the right. And notice that there's 3, 7, 2, and 2. So that's 7, 8, 9, 10, 11 misclassifications. And that's it. So it does okay. But note, if you go back and watch all the videos in chapter 7, quadratic prediction, the quadratic classification function, actually did the best of all of these. And that's probably why it's the most used classification function. Okay, well, I have to stop. We're at 15, 16 minutes. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.